Imagine, just for a second, that you are Apple. You're gearing up to launch the highly anticipated iPhone X, and you've got a starting retail price of $999. But here's the catch. Before a single piece of glass is cut or a microchip is even soldered, you need to know exactly how much that phone is going to cost to manufacture. Well, the estimated production cost of that iPhone X was around $412.75. That means it was about 59% cheaper to make than its actual retail price. But this raises a really fascinating mystery for us to explore. How do these massive companies accurately predict those costs months, or honestly, even years before manufacturing actually begins? How do you put a hard, reliable number on a future that hasn't even happened yet?
Welcome to This Explainer. Today, we are focusing squarely on Module 3 cost estimation techniques. We're going to uncover the invisible frameworks, the step-by-step methodologies, and the heavy lifting math that engineers and economists use to turn unpredictable, risky future projects into concrete financial estimates. Honestly, whether you're building a smartphone, a massive logistics hub, or a power plant, the rules of engineering economy are absolutely going to apply.
Okay, let's dive into this. Here is our roadmap for today. 1. The 7 essential steps. 2. Mapping projects with WBS. 3. Estimating cash flows. 4. Cost-price indexes. And 5. The power of learning curves. Section 1. The 7 essential steps, a roadmap for uncertainty. Whenever you're tackling a major engineering decision, maybe you're choosing a new high-efficiency furnace or buying a whole fleet of corporate jets, you are fundamentally grappling with two things: time and uncertainty. Let's be real, human beings are notoriously bad at estimating how much time and money things will actually take. To manage that chaos, engineers rely on a very disciplined 7-step procedure. It starts with defining the exact problem and developing feasible alternatives. Then, you map out your prospective outcomes, pick a decision criterion, analyze and compare those options, and make your final selection. But honestly, the real magic is in step 7, performance monitoring. You always have to look back and evaluate the results to see if your estimated future actually matched reality. Section 2. Mapping projects with WBS, the project skeleton. So how do we organize all the incredible amounts of data you need for those 7 steps? I mean, if you just start guessing at costs, you are inevitably going to miss something crucial. Enter the work breakdown structure, or WBS. Think of it like the project skeleton. It's kind of like packing for a massive cross-country move. You break things down by room, then by piece of furniture, then by individual box. The WBS does exactly that. It divides physical and functional work elements into increasing detail. The total resource requirement for any broad category is literally just the sum of all the tiny, detailed sub-elements below it. The entire point of this structure boils down to one golden rule, which is, it ensures all cost elements are defined and categorized. Because, as any seasoned engineer will tell you, the absolute most expensive mistake you can make is simply forgetting to budget for a crucial piece of the puzzle. The WBS is your non-negotiable foundation to prevent those catastrophic blind spots. Section 3. Estimating cash flows. Adding the numbers. Once we have our WBS skeleton mapped out, we need to start hanging the actual numbers onto those bones so we can estimate future cash flows. There are basically 2 primary ways we do this. Top-down estimating is kind of like looking at the whole cloud. It relies on historical data from similar past projects to get a broad estimate early on when your plans are still being refined. Bottom-up estimating, on the flip side, is looking closely at the individual bricks. It breaks the project down into those small, detailed WBS units and estimates specific costs once the final product is clearly, rigidly defined. Now notice how estimating techniques literally act as a bridge here. They seamlessly connect the categorized, theoretical structure of the WBS on one side directly to the detailed cost and revenue data on the other. It's the absolutely crucial link between conceptual planning and hard, finalized financial projections. Section 4. Cost-price indexes, the heavy lifting math. All right, let's zoom in. Frameworks are great, but eventually you actually have to do the math. The biggest problem estimators face is that time passes and inflation happens. Costs just don't stay frozen in time. Enter the cost-price index. Instead of getting super bogged down in the algebra right now, the concept is beautifully simple. It updates historical data. You take a known past cost and you multiply it by the ratio of today's index over the old index. This mathematically adjusts the price of absolutely anything, from raw steel to manufacturing labor, based on changing economic conditions.
To see this in action, let's look at a quick story about Acme Chemical. Back in 2002, they purchased a huge industrial pump for $112,000. To figure out if this made economic sense, they tied their cost estimating to an industrial pump index. The baseline for this index was exactly 100, established a full decade earlier in 1992. By 2002, that index had risen to 212. By applying the cost price index, they could accurately translate the value of those dollars across a whole decade of economic change.
But what happens when we need to account for time and a change in size? Take Acme Logistics. They built a 36-door cross-docking hub 10 years ago for $6 million. Today, they want a larger 48-door hub. Obviously, you can't just multiply the cost linearly. First, they use the index to update the old $6 million to today's money, bringing that base to about $8.3 million. Then they apply a capacity factor of 0.82 to account for economies of scale. When you do the math on the ratio of those sizes, they arrive at a highly accurate estimate of just over $10.5 million for the brand new, larger hub. The really crazy part is realizing that this exact same mathematical logic scales up to some of the largest structures on Earth. When predicting costs for colossal infrastructure like a skyscraper or a massive energy facility, the stakes are astronomical, but the power sizing model remains the key. You're taking a known historical reality and mathematically bending it to fit a larger, much more ambitious future.
Check out this incredible example of scaling up a power plant. An aircraft manufacturer knows a smaller 200-megawatt plant cost $100 million 20 years ago. Well, they want a massive 600-megawatt plant today. First, they update that old price tag using the cost index, which brings the modern baseline up to $300 million. Then, they apply the power sizing model to account for the huge increase in scale. The math yields an astounding yet incredibly grounded estimate: $714 million.
Section 5. The Power of Learning Curves. Human Efficiency. Finally, we have to talk about the human element, because unlike static, predictable machines, human beings learn and we adapt, which drastically affects future costs. And this brings us to the learning curve. The core concept here is wonderfully simple. The more we do something, the faster and better we get at it. Think about the very first time you tried to assemble a piece of complicated IKEA furniture versus, say, the 5th time. Huge difference, right? As production volume increases, the input resources required per unit naturally drop.
But costs don't just drop randomly. Engineering economics demands predictability. The essential rule of thumb here is that a constant percentage reduction occurs every single time the total number of units produced doubles. It's this beautiful, predictable, mathematical rhythm of human efficiency that absolutely must be factored in to ensure a company prices its products correctly over a complete life cycle. And that brings us to the end of our journey through Module 3. We've seen how engineers use the 7 steps, the structural rigor of the WBS, the heavy lifting math of cost indexes, and the human reality of learning curves to peer into the future. But I want to leave you with this final, provocative thought based on everything we've talked about today. With all these brilliant frameworks, we can accurately calculate the cost of materials, labor, and scale. But in an increasingly fast-paced and unpredictable world, how do you truly put a final price tag on absolute uncertainty? Thanks for joining me for this explainer, and keep questioning the math behind the world around you.